Hello, folks. Today, I would like to launch into a more in-depth discussion of minerals. We've seen the definition, but let's talk about a little bit more about them and launch into learning about some specific minerals that are important at Earth's surface. So in this opening image, we are looking at the mineral quartz at many different length scales, building up from the silicate tetrahedron, where this atom right here is silicon and this one is oxygen. And if you build those up into a particular repeating pattern, and then you build those 2D layers into a 3D pattern at a certain scale, you'll notice that you are building the mineral quartz, and that this looks a lot like this, but that if you look at the atomic scale, this is maybe 20 atoms tall, whereas in even the most microscopic crystal, it's probably 100,000 atoms long in the same direction. So we build up bigger and bigger to crystals we can see with our naked eye. You might have 10 million to a billion atoms along one of those lengths. And then if we look at a beach that's mostly made of quartz sand, tiny microscopic or close to microscopic crystals of quartz make up these sand grains. That might be 100 billion atoms from where you're standing here to the edge of the beach there. These are all different ways of looking at quartz. And it turns out that understanding what's going on the microscopic scale on this end is going to explain a lot of what goes on the macroscopic scale in these other pictures. So we're going to start to think about how that is, and we're going to look at quartz in some detail and other related minerals. So we're going to talk about the definition of a mineral and review that. You should know that after this lecture. You should be able to regurgitate that pretty well. I'm going to talk about the process of chemical bonding and how that controls the properties of minerals. We're going to talk about how microscopic patterns, the way that the atoms are connected to each other, make macroscopic, so right, microscopic being the opposite of macroscopic, properties. Macroscopic things are things that you can see without a microscope, right? Things in your everyday life. And we're going to talk about how the way that atoms build on each other in minerals controls the macroscopic properties of those minerals. We'll also talk about the important mineral properties that we could diagnose in a lab setting. Next, we'll talk about classes of minerals, and then we'll focus on the silicates because that is an important and major class of minerals at Earth's surface. So as a reminder, what is the definition of a mineral? Remember that it's got to be natural, it's got to be solid, it's got to be crystalline, that is, have a repeating 3D pattern to the structure. It's got to be inorganic, not made of complex carbon compounds. It can be made of very simple ones, but it can't be complex carbon that comes from organic life. And minerals have to have a very specific or narrow range of chemical compositions. You have to be able to write a chemical formula for them. So let's look at how that applies to quartz. Minerals are naturally occurring. Well, these natural features, such as beaches and crystals forming in ore veins, indicate that quartz is a naturally occurring substance. Minerals are solid. You can see a lot of evidence that these quartz crystals here are solid. They're certainly not liquid. You might have some liquid in the background there, and that water is not a mineral, and the air in the atmosphere is not a mineral. But the solid sand, each of those particles, it's a particle of mineral matter. Minerals are crystalline, so we can look at a substance on a macroscopic level. If we look at a crystal of quartz, the thing that tells us, that suggests at least that it's crystalline, is that it makes these regular geometric shapes, right? So we've got kind of like this prism with rectangles on the border, and it's a hexagonal prism terminated in these triangles here. The fact that it's got such a regular repeating structure is a good indication that its microscale structure on an atomic level is also going to be regular and repeating, which is what means it's crystalline. If we look at an atomic view of such of the structure of quartz, we can see that regular repeating structure. You can see it repeat, this tetrahedron here, repeats over here, repeats over here, and then it repeats in this dimension as well. And we can imagine it repeating down into the plane of the page as well. And if you build those up into a bigger structure, you can see that this very microscale crystal starts to have the same sort of geometric patterns that end up in the macro scale structure. Minerals are inorganic. Well, in some cases, you're just going to have to take our word for it because we're not doing any sort of mass spectrometry or X-ray diffraction analysis in this class to reveal anything about the components of these structures. But for something like quartz, it's inorganic because it's made of inorganic compounds. There's no complex carbon compounds in here. It's all silicon and oxygen, so it is inorganic. Minerals have specific chemical compositions. And once again, you're going to have to take our word for it a little bit. But for example, quartz, we can write as SiO2. This 2 is indicating how many atoms of oxygen there are in the structure. And if there's just one, it's implied, it's not written. So what this structure of quartz means is that there's 1 silicon for every 2 oxygen. That might be hard to square with this component of the structure down here, this tetrahedron, where we see 4 oxygens for each silicon. Let's talk about that just a little bit. So in this silicate tetrahedron down here, we see 1 silicon and 4 oxygens. How does that build up into a structure that's made of 1 silicon for every 2 oxygens? Well, if we look close in here at, say, this oxygen here, we'll notice that it is shared between 2 silicons. So for every oxygen, we've got 2 Si, right? So we've got a silicon here and a silicon here. For this oxygen, we've got 2 silicons there and there. So if for every 1 silicon we have 4 oxygens, but for every 1 oxygen we have 2 silicons, then if you reason for it for a little while, you'll realize that you have to have 1 silicon for every 2 oxygens overall in the structure to get things to balance out. Thinking of it another way, if we looked at this tetrahedron here and we started to draw in another tetrahedron that it was attached to, so it's attached to that silicon, which is attached some more oxygens, each one of these oxygens is going to be attached in such a way. It's in this framework structure. So in principle, we could sort of divide these oxygens in half and say 1/2 of the oxygen belongs to this silicon and the other half belongs to the other silicon. And if we do that for each of these, we would see that we have 1 silicon and then we have 1/2, 1, 1.5, 2 oxygens for this silicon. Once again, we get back to the same thing. It's the specific chemical composition that makes it up. In addition, in quartz, we're never going to have any sort of major substitutions that go on. We're not going to replace the silicon with iron, and we're not going to replace the silicon with magnesium or any other atoms, and we're not going to replace the oxygen with sulfur. In other minerals, there is a small amount of substitution allowed as long as you can specify the ranges. But in some minerals, that chemical composition is exact. Even in the ones where you have a little bit of substitution, it's not a whole lot. It's not as if, you know, anything can substitute into a particular site. So at this point, you should be able to stop and tell me the 5 qualities that determine if something is a mineral, the 5 parts of that definition. Think about it for a moment and see if you can come up with all 5. If you can't, you should go back and study past material because you're going to get asked about this. For those of you playing along, it's got to be natural, solid, inorganic, crystal structure. Sometimes I'll just write XL, crystal. And it's got a specific chemical composition. Those are your 5. For something to be a mineral, it's got to meet all 5 criteria. Let's think about the stuff that makes up minerals and really all matter. Matter is made of atoms. Those are the smallest constituent pieces of everyday matter. and that those atoms are connected together by certain types of connections that we call bonds. Okay, so first let's talk about what atoms are. Atoms, at least to a first approximation, you sort of think of as kind of like a little solar system. You've got a nucleus in the center, and it's got a positive charge because of the protons that make it up. And then around that, we've got a bunch of electrons, negatively charged particles. And so the physical law that's controlling the structure of these atoms is the fact that opposite charges attract. So the plus of the nucleus is attracted to the minus of the electrons. And there's some weird quantum mechanics stuff that happens in there to make it so that these don't actually end up running into the nucleus. But the important thing is that we've got a positive nucleus and negative electrons. And those things attract to one another. Bonds are really just an extension of that idea that opposites attract. In certain situations, you can get pieces of each of these atoms being attracted to one another. And those are called bonds. So in an ionic bond, what happens is one atom, in this case chlorine, steals an electron all the way away from sodium. Because it steals that negatively charged electron, this atom, which used to be neutral, has an overall negative charge because it's stolen that electron. And this atom, which used to be neutral, has an overall positive charge. We call these ions now. And that's why we're going to call it an ionic bond, because they're missing some of their original electrons. They have a net charge to them. As a result, because this ion overall has a positive charge and this one overall has a negative charge, those ions in turn are attracted to one another. And that attraction is what we call that ionic bond. In a covalent bond, like down here, these might be, let's see, this is probably atoms of chlorine. So if we had one chlorine and another chlorine, those atoms, one of these atoms can't rip an electron away from the other one because they both want the electrons just as much. And you learn about that a lot in a chemistry course. But for us, what we want to note is that this covalent bond type, the electrons are shared. So they're not totally stolen, but they sort of share and overlap their sets of electrons. And now this chlorine is attracted to all, the nucleus anyway, is attracted to all the negative electrons. And the nucleus on this one is attracted to all the negative electrons. And you do also have like charges that are repelling. These are repelling each other a little bit, and the electrons are repelling themselves a little bit. But overall, the sharing of these electrons ends up resulting in an overall attraction. That's still because of that general principle that opposite charges attract. It's just that on a covalent bond, electrons are shared. So let's talk about how that affects minerals. The mineral halite, also known as sodium chloride, which makes up your table salt, is made of sodium ions with a positive charge and chlorine ions with a negative charge. They're attracted to each other, and so they bond together. But the ionic bond tends to be weaker in strength. And as a result, sodium chloride tends to break relatively easily. It's what we call soft. And it also dissolves easily. In contrast, minerals that are made of covalent bonds tend to be stronger. So we've already talked about quartz, and it's made of silicate units, this Si here and this O here. Many of these minerals have all silicate minerals are going to have silicon and oxygen making them up. And the bond between those that we often draw as a stick is a covalent bond. So these covalent bonds, which we draw as sticks, tend to be very strong. And that's going to control the properties of these minerals. One thing that I'll note is that microscopic patterns make real world properties. We used the term macroscopic before. That is things that you can see with your naked eye. You don't need a microscope to see them. And I just say real world here to remind you that what's happening on a microscopic scale matters to properties that you can see in everyday life. So if we look at different angles at the structure of this quartz, we'll actually see some symmetry start to result. We can sort of start to see the four-sided symmetry here in the way that the holes in between the atoms are arranged. And if you look at it in a different direction, you see some six-sided symmetry resulting in the holes between the atoms, or even between the atoms themselves if you look closely. Turns out that that ends up building up into the real-world symmetry of the quartz crystal. You can see that four-sided shape here, and the edge, at least, of the six-sided shape here. We continue underneath like that. 1, 2, 3, 4, 5, 6. The different orientations of these atoms and how they're connected to each other controls the symmetry of the minerals. So we can start to see this is one example of a microscopic pattern, the way in which the atoms are arranged, making this real-world property, the symmetry. Another way in which that happens is, as we talked about, quartz has a lot of strong covalent bonds. And these bonds are really in all directions. Like if you looked at this structure, there's lots of bonds that way, that way, that way. If you even went this way, there's still a lot of bonds going in every direction. There's no planes of weakness where you could cut easily. And as a result, it makes the mineral quartz hard to break, meaning that it has high hardness. It also contributes to the fact that it weathers or breaks down at Earth's surface very slowly. Remember that for later. Quartz, as a result of the bonds in it, tends to have high hardness and it weathers very slowly, breaks down slowly under Earth's surface conditions. It doesn't dissolve, not easily anyway. So I want to focus a little bit more on how crystal structure can matter. It's not just the stuff that makes up a mineral, but how those atoms are rearranged. So we've got two different minerals here that actually have the same chemical composition. Graphite is the stuff that makes up your pencil lead. And as you know, you can scratch that pencil lead on something as soft as a piece of paper and leave bits of it behind. It's very soft, meaning it must have some weak bonds. In contrast, diamond is the hardest structure, natural structure known. Probably has strong bonds. Surprisingly, both are made entirely of the element carbon, with nothing else in it. So how is that the case? Well, it comes down to the crystal structure. If we look at the way in which the atoms stack together let's start with the diamond this time. You can see bonds in every direction. Turns out these carbon atoms make tetrahedra as well, where each one is connected to 4 others, and those connections lead off in every direction. Lots of strong bonds in every direction. This one ends up being hard as a result. In contrast, graphite is actually made up of sheets. So like here's a sheet here, and here's a sheet here. Within those sheets, you've got a lot of strong covalent bonds that extend in most directions. So within a sheet, the bonds are very strong, but between the sheets, the distances and the bonds themselves are much weaker. Because we have a plane of weakness here and a plane of weakness here, this ends up being relatively weak and soft. And you can break this mineral apart along those planes of weakness. A word for two different minerals with the same composition but different structures is this, polymorph. So graphite and diamond are polymorphs of one another. As we've seen, because mineral properties match their atomic structure, that means something. That means that if we test the mineral properties, we can figure out what mineral it is based on how those properties match up to a list of known properties, depending on the microscopic structure of each mineral. And so we're going to learn a little bit about how to do that, at least over time in this course. I'll show you one more example of a mineral that we're going to get familiar with. This is biotite. It's a type of mica. It has this dark color, and it peels into thin sheets, the edges of which you can see here. It's very soft. You can scratch it with your fingernail. And much like graphite, it is made of sheets of atoms. So we've got sheets of silicon and oxygen and some other stuff like aluminum, bonded together with strong covalent bonds that we've drawn here with cylinders. But each of these sheets is separated by ionic bonds at best to these potassium ions. So we've got weak bonds here, strong bonds within each sheet, and that means that it's much easier to peel the sheets apart. The structure of mica and the fact that you can scratch it, it's soft, and peel it into sheets is all dependent on the microscopic structure. So here's a summary of that. Mica has strong silicon-oxygen bonds, much like quartz, within the sheets. Other covalent bonds as well are strong, but it has those weak ionic bonds between sheets. And much like a chain is only as strong as its weakest link, a mineral is going to be only as hard as its weakest bonds allow it to be. So biotite mica, easy to peel apart, has low hardness, and it will also weather faster than quartz. So here are some important properties that we will start to learn about and that you're going to revisit in lab. But I want to mention some of them here. So we've already mentioned hardness, how easy it is to scratch and break minerals. Cleavage and fracture are how those minerals break once they do. Do they break into geometric patterns? Or do they break irregularly? Or sometimes do they break curved? Luster is the type of shininess it has. But not just is it shiny or not, but we might ask, is it shiny like a metal is shiny? Is it shiny like a pane of glass is shiny? Is it sort of shiny in the way that wax is a little bit shiny? Or is it totally dull? And there are other terms that we can use for luster. Color is self-explanatory. Streak is the color of a powder of the mineral. Turns out that that is a better representation than color in some cases. Sometimes the powder is going to have a different color than the mineral itself. Density, how heavy is it for a given size? That matters because some elements that make up minerals are way more dense than other ones. Crystal habit is how a mineral grows. So sometimes the shapes that a mineral makes while growing are different than the shapes that it makes when it breaks. So crystal habit is shapes as it grows. Cleavage and fracture are shapes when it breaks. Two properties that will occasionally matter are magnetism. Is a magnet attracted to it? And does it react with a little bit of acid? Does it fizz when we put acid on it or react in some other way? And here's a summary if you want to study each of these, just to have a study tool. You might come back and look at the slide.